we have f of x equals x minus 1 squared times e to the x. So this particular function has double root at x star equals 1. Therefore, what's the problem we're going to run into with this one?
The prime of x star would be 0, right?
Right. Okay. So the previous convergence analysis doesn't apply here. So we'll take a look at the convergence analysis if we have a double root. So we've got ek plus 1 is equal to xk plus 1 minus 1 instead of x star. We just have minus 1 because x star is equal to 1. So now we've got xk minus f of xk, which is just xk minus 1 squared e to the xk all over f prime at xk, which is 2 xk minus 1 plus xk minus 1 squared times e to the xk, and then all minus 1. Okay, so this is our expression for xk plus 1 right here. So right off the bat, we see that those guys can cancel right there. And then also, we've got xk minus 1, so those combine together, and that's going to be just ek. So we've got ek minus, and then xk minus 1 we can replace with ek right here too in the numerator. So we've got ek squared, and in the denominator, 2 times ek plus ek squared. I don't even need those parentheses. So, okay. And then we see we can cancel this. Well, before we do that, I can, alright, so what I'm going to do is factor out an ek out of the whole thing. So then I have 1 minus ek all over 2 plus ek. Well, let's leave it in here first, and then I'll factor it out of this expression in just a second. So factored out the ek. And then we have 1 minus, and so now I'll pull the ek out of the numerator and denominator of this fraction, and that leaves me with 1 over 2 plus ek. So now I can cancel those. And this is 1 minus 1 over 2 plus ek. And then ek we can write as 1 minus 1 over 2 plus xk minus 1. And then come around here. And so now I can combine like terms here, and then I can get a common denominator and simplify. So we've got EK. When I combine like terms, I get EK plus 1 down here. I mean XK plus 1. So we have XK plus 1 over XK plus 1 minus 1 over XK plus 1. So now I can subtract my numerators. And I've got XK plus 1 minus 1 all over XK plus 1. So now my 1's cancel. I'm left with EK times XK over XK plus 1. So that's what we arrive at. If we choose x sub 0 greater than 0, then Newton's method converges to the solution x star equals 1 linearly, and the asymptotic error constant c is equal to 1/2 if we choose our x sub 0 this way.
If you choose x sub 0 to do what again?
Oh, sorry. If x sub 0 is greater than 0. Okay. So that's all for Newton's method. Now we'll move on to the secant method. So the reason we have, or one particular drawback for Newton's method is that we have to compute f prime at xk, and sometimes that might be difficult for a particular function. If you don't want to compute the derivative of the function, then you definitely don't want to use Newton's method. The secant method is a solution to that problem. And so the secant method also avoids the issue by using the finite difference to approximate the derivative. This means that f of x is approximated by a secant line through 2 points of the graph instead of just a tangent line which goes through 1 point. Now the secant line approaches the tangent line the closer that you get to the solution, but also with the secant line, since we're using 2 points on the original function to approximate it, then it's necessary to choose 2 initial guesses, x sub 0 and x sub 1. And then the next iterate for the secant method is obtained by computing the x value at which the secant line passes through the points. So the secant line will pass through the points x, or x sub 0, f of x0, and x1, f of x1, where this has where through these points where they have a y coordinate of 0. So to figure out what our next iterate would be, we'll look at this, f of x1 minus f of x0 all over x1 minus x0, and then x2 minus x1 plus f of x1 equals 0. So if we solve this for x2, then we're going to get the formula that we can use to get our next iterate. So if we solve this for x2, we'll get x1 minus f of x1, x1 minus 0 all over f of x1 minus f of x0. So this is to compute x2. Now we can put this in terms of xk, which we'll do when we get to the algorithm.